Log on, tune in, find out. Another good idea from Cambridge.
So, the last talk today is by Carola Schönlib. Carola studied in Vienna and with Peter Markovich, and when Peter Markovich moved to Cambridge as now our new professor of applied mathematics, she moved with him, got her PhD here, then moved to Göttingen to a postdoc, and last year has been elected to a lectureship in applied and computational analysis at DMTP.
All right, thank you. Microphone. Okay, does it work?
Yes.
Yeah, okay. So thank you, Arya, and thanks for the invitation. Before I start, I would like to just draw a picture which kind of summarizes what I want to tell you in this lecture. And even if you stop following me after I've done this, after I actually go on with the lecture, just having this in mind is already good. So what I want is, I have given an image, and I call this image G, and this image that I observe is the original image U, which I want to reconstruct, after it has gone, say, through some linear process, which I call T, and we have seen before the T being the same as A in what Emmanuel Candes said. And I have this, and I might even have some additional noise, which I call M. And in particular, what I'm interested in is in situations where this G, the image that I observe, is huge, has a very large dimension, and saying that I have an image G which is defined on some spatial domain omega, like say for now, because I cannot otherwise draw it very good on the blackboard, this image domain omega is in R2, maps this domain omega into, say, the real numbers, and the domain omega, usually with images, is just a rectangular domain. And meaning that G is of large scale means that my domain omega on which G is defined is very large. So there are a lot of pixels involved. Say I have an image which is 5,000 times 5,000 pixels. Okay. And now the strategy is the following. So in some sense, I want to reconstruct U from the observations that I make, which are denoted by G. And so what I have to do is, to do this image reconstruction process, I have to process the image. So this is a process. And this is very expensive if the dimension is large. So one specific approach that I want to discuss with you today is, instead of solving this image processing task on the whole image domain, which is large, I split the problem into smaller problems, and I solve the problem on each small problem. So I split the domain omega, say, in two domains, omega 1 and omega 2, and I process the image on omega 1 and omega 2, and then stitch together the solutions. Okay, so that's the main idea of what I want to talk about today. All right. So how do I want to process this image? The main method of interest for us is, I want to process the image by solving an optimization problem, which is non-smooth and convex in general. And the specific problem that I want to solve is, I want to find a reconstructed image U that has minimal L1 norm of its gradient. So in other words, when we talk about compressed sensing again in this language, I want to find an image U whose gradient is sparse. And I want to find this image U under some linear or nonlinear constraints For example, a linear constraint would be that the L2 norm of G minus TU should also be small. All right. And since I'm talking about large-scale problems, and this is the idea what I've drawn here, I want to solve this problem not at once, but I want to solve it by splitting it into two smaller problems. So here I'm solving a reconstruction problem for U. I've given this image G. I have this linear constraint that that TU minus G in the L2 norm should be small, and I'm searching for an U which is sparse with respect to its gradient. And I do this not on the whole domain omega, I'm minimizing this on omega 1 and omega 2, and then I stitch together the solution. All right, so just to give you an idea of the kind of point of view that I have on this, I just give you some references. So basically this domain decomposition, or a more general subspace decomposition idea, was evolved together with two colleagues of mine, Massimo Fornacier and Andreas Lange, who are both from RICAM in Linz. And what we are doing here is basically we are coming up with the subspace decomposition method for for the minimization of the L1 norm of the gradient, together with some numerical analysis that actually tells us that what we get through the solution of this domain decomposition problem is the solution, is the minimizer U of the problem on the whole domain, which is not something that comes to you for free. And there are some additional papers where we talk about applications in large-scale imaging problems, like here, applying this to an application in parallel MRI. And there are also some accelerations of this method by modifying the way how we solve the subminimization problems on each of these small subdomains omega I. All right. So what are the challenges that we face when we want to consider such non-smooth convex optimization problems, and in particular when we want to solve them via subspace decomposition methods? Well, the standard numerical analysis in both cases fails. So for non-smooth problems, you have to consult different mathematical tools, and here it's just some keywords. So what the kind of analysis that we do heavily relies on results from convex analysis, from variational calculus, from geometric measure theory, like when we deal with the L1 norm of the gradient of U, which is also known as the total variation of a function. We are dealing with issues when we want to apply domain decomposition methods for these problems, because functions U which have a minimal total variation are, as I said, non-smooth, so they can have jumps, and these jumps can also cross the interface of these domain decomposition patches that come out of this decomposition here. So I have to somehow deal with those issues. And again, there are some keywords here, like iterative thresholding, Douglas-Rechford splitting, things like this that I have to use in order to deal with these, with this special situation. So again, you cannot see it really, but what we do is we look at the Chev-Logan phantom, and as we have heard in the lectures during these last days, what we have usually in magnetic resonance imaging, the datum that we measure are sampled Fourier coefficients of the function of the image function u that I want to reconstruct. And I reconstruct this function by putting some a priori information into the game. And this a priori information, in our cases, we assume that the image that I want to reconstruct is piecewise constant, which is just another term of saying that the function u has a sparse gradient. And then, so meaning that the function u is sparse in its gradient, which, as we have also heard during these last days, is in general an NP-hard problem. So what I do is I relax it, and that's how I arrive at this L1 or L1 gradient of u minimization problem, which is also known as total variation minimization, and we will also talk about this. All right, so this is the general framework where I'm in, and I'm concentrating on this case that I want to solve problems where I minimize the total variation, the L1 norm of the gradient of u. So, brief outline of what I want to do. First, I want to give you some examples of large-scale problems in imaging. I will talk a little bit more about the total variation, which goes beyond the explanation that the total variation is the L1 norm of the gradient of u. It's something actually more general. The L1 norm of the gradient of u is a special case of the total variation. And we will talk about how to solve minimization problems which promote sparsity in the gradient of u, meaning total variation minimization, how we can solve this for large-scale problems by splitting the problem in smaller problems. And here we will talk both, depending on time, actually, we will talk both about decompositions, subspace splittings where we decompose the special domain, but also what we can do is we can do something more general where we not decompose the physical domain, but we might decompose the wavelet. We might want to say we have a function u which has a multi-resolution analysis, and corresponding to this multi-resolution analysis I have a sequence of orthogonal subspaces which are the wavelet spaces, and I want to decompose with respect to the wavelet spaces, for example. And we will also see how this works. And last but not least, I will give you some hopefully convincing numerical results of how this strategy is speeding up the total variation minimization for large-scale problems. And in particular, how this can be speeded up when you parallelize your computations. All right, so what is large-scale imaging? Large-scale imaging, first of all, comes to us nowadays quite often when we are in the hospital, because a lot of these fancy medical imaging machines, they can produce nowadays huge data sets. In magnetic resonance imaging, you have, in the meanwhile, 3D imaging. You can have diffusion magnetic resonance imaging, where additional to your spatial dimensions, you also have directions in which the diffusion goes. So you have two additional dimensions. You have positron emission tomography or single photon emission tomography, where you might have even 4 dimensions. So you might have 3 or 4 dimensions, 3 dimensions in space and 1 additional dimension in time, where you have, for example, dynamic PET or things like this, where you can where you have a movie and you follow the beat of your heart. And there are many other fields where you might come across huge data sets, like astronomical imaging, global terrestrial seismic tomography, or something that my heart lies in very, very much, is arts applications, where you have digital images of a piece of art that is damaged in some sense. So here, I don't know if you can see it very clearly, but here this is an image of a fresco which is destroyed in some parts and these white dots. And what we want to do is we want to reconstruct this digitally. So we want to create a digital reconstruction of this. And usually you want to have high resolution images to do this, to get the most information out of your image. So what are the computational issues when you deal with large-scale images? So first of all, usually iterative methods which are going to solve your image reconstruction problem numerically can be arbitrarily slow, and there is a nice work by Loris where he's actually discussing this. There are accelerations of the usual iterative methods, where I've listed some of those accelerations here, where basically these accelerations deal with preconditioning the operator, well, say your iteration matrix in such a form that your iterations decay faster, your iteration error. But all of those, even all of those accelerations, they are all of sequential nature. And when they come to extremely large scale problems, none of them is able to address the reconstruction process in real time or even efficiently. And another thing with the non-smooth optimization problems is that they scale very badly with the dimension, meaning that if you say linearly increase the dimension of your problem, it might be that the convergence time or the number of iterations that you have to do to arrive at your minimizer even increases much more than this. All right. So the strategies, as I've said, we are interested in to tackle this are splitting techniques, and above all, what we are going to talk about are subspace splitting techniques, where the idea is that we split the problem into problems of smaller size, and then basically what you can do is you can apply your favorite, iterative method, preconditioned iterative thresholding, or what you would like to solve the smaller problems that you get out of this. And the splitting technique actually has two effects. The one is that you have to solve problems which are of smaller size, which, if you parallelize your computation, everything goes much faster. But it can also, in certain situations, like when we talk about the wavelet decomposition, it can even have a preconditioning effect, meaning that the iteration matrices that are related to your subspace minimization problems are better conditioned. Okay, so it has these two things. And when we talk about these splitting techniques, what we want to find splitting techniques which produce an iterative sequence of solutions that really converge to a minimizer of the functional on the whole space, on the whole physical domain, where my minimization problem is defined. So, total variation minimization, being a little bit more specific than saying it's the L1 norm of the gradient of u, what we want to solve is this. We have functional j. We want to find, we have given a datum g, which is what I've written here. G is the original image u after it was distorted by some linear process t plus some noise. And I want to recover u as a minimizer of this guy here, where here I've replaced now the L1 norm of the gradient of u by this. And this is called the total variation of u. And the total variation of u is, to be more specific, is basically the total variation of the finite radon measure du, where du is the derivative of u in the sense of distributions. So basically the total variation of u is the total variation of a measure. And this measure is the weak derivative of u. And this is very important actually, because just talking about the L1 norm of the gradient of u, your solution actually has different properties than minimizer of the total variation, because, and then this is the nice thing about it, the total variation actually can have minimizers which are singular, which can have jumps, which the L1 norm of the gradient of u, if you panelize a function with the L1 norm of the gradient of u, it cannot have jumps anymore. So a minimizer of the total variation is singular, so it makes sense actually to stay with this more specific definition here, because what we actually want when we apply a reconstruction process to an image is we want to reconstruct an image which preserves the edge set, and that's the second point. Jumps in an image are actually the edge set in an image, and the edge set in an image is something that characterizes the image the most, right? This is everywhere where something changes from black to white or something like this, you have a jump. And you want to preserve these things, and the total variation is actually preserving those. And to go back again to the L1 norm of the gradient of u, this relation is actually true if you have a continuously differentiable function. And it's even true if you have a W11 function, but then you have here the distributional gradient as well. Okay? So that's important. So we want to apply total variation minimization to images because we want to preserve edges on the one hand, and we want to preserve only a small number of edges. Okay, we only want to preserve the most characteristic edges in an image, because other edges which are created by small oscillations, those we want to kill. Okay? All right. So that's why sparsity in the gradient of u, right? We only want to preserve a small number of discontinuities. All right, and of course, because this is a very, very famous and very popular reconstruction method in imaging, there are loads of methods, numerical methods, with which you can solve this. And you're not supposed to read all of this now, just to show you the kind of, spread out literature that exists on this. Two things that we are actually going to use to solve our subminimization problems is iterative thresholding, and another thing with which we can speed up the subminimization problem is Bregman iteration. We will see this. That's why they are highlighted, so you might want to keep them in mind for later. However, there are a lot of efficient, and they're very efficient methods. I mean, for example, the split Bregman method, I think, is one of the, well, it's actually right now, at least Osher is kind of claiming this. So, but it's actually now the fastest method to solve total variation minimization. So, and it is very fast. But the problem is, if you have large-scale problems, these methods will still break down because of their iterative nature. So that's really the whole problem, because these non-smooth minimization problems are usually solved iteratively, and that's why we have to pay a lot of computational money, say, to solve them if they are large. And again, there are some examples. I'm not going into this. One example that we will encounter later is parallel MRI, where I have additional to the spatial dimension, say if I do 2D MRI, I have an additional 12 images of the same size, which are representing the so-called coil sensitivities. We'll talk about this a little later. So you see the problems that we are going to deal with are very large. And that's why we want to solve them by subspace decomposition. All right, so what's the idea now, additional to this picture? What's the idea in mathematical terms? So in general, you know, going away from the specific case of the total variation for a second, what we do is we want to reconstruct u as a minimizer of this function where psi of u was the total variation before, is some regularizer right now, and I have a fitting between the datum and the original image u. And what I want to do is I want to minimize j, and I want to minimize j on a Hilbert space H. And instead of minimizing it now on the whole Hilbert space H, I split this Hilbert space into two orthogonal subspaces. I show everything here in mathematics for two subspaces, but just because, you know, it's easier. Everything generalizes for multiple subspaces as well. So I do this now. I split it into two orthogonal subspaces. And one thing that I might have is that if I split those, this Hilbert space H into these orthogonal subspaces, my problem might not split additively. You know, it might not split like this, that psi evaluated in the projection of u on v1 plus the projection of u, this should be a u, on v2 is not the same as psi evaluated in each of these guys. So, and this is in particular true for the total variation. We will see that this is a crucial point of proposing domain decomposition methods for non-smooth problems, because you might not have this additivity property. Okay, so just keep this in mind. We are considering the general case where we might not have that my functional splits additively with respect to this decomposition. So, what I want to do then is, if I have split the problem like this, instead of minimizing j on whole H, I minimize it alternatingly on each of these orthogonal subspaces. So I create a u1, which is the minimizer of j on the subspace v1. I create a u2, which is a minimizer of j on the subspace v2. And then I add them up. So I stitch those two pieces together, if you want, here with a domain decomposition. v1 would be, say, L2 of omega 1. v2 would be L2 of omega 2. And then I have u1 here, which is u projected on omega 1. u2 here, which is u projected on omega 2. And I approximately solve these two minimization problems, stitch together the solutions, and iterate. Okay, so that's the basic strategy. Question is how to do it such that the sequence actually converges to a minimizer of this functional. All right, so again, the motivation of doing this is a preconditioning effect, and you can think about a preconditioning in terms of subspace decomposition as something like block preconditioning. Okay, so you can keep this in mind. I don't have time to talk more about this. And of course, we hope that we can accelerate our computations by means of parallelization. All right. So one example where everything is quite well understood is for L1 minimization. For L1 minimization, the nice thing is that actually we have more than in this general situation, because for L1 minimization, if I have a function u, which is u1 plus u2, okay, which is the projection of u on the subspace v1 plus the projection of u on the subspace v2, where v1 and v2 are two orthogonal subspaces of the Hilbert space H. What you have, if you compute the L1 norm of u, this actually additively splits. So this is the L1 norm of u1 plus the L1 norm of u2, which means that if you now split the problem,
but it's only v1 and v2 are coordinate axes, because if not, it's not.
So it's only if, say, if U is a sequence defined in some index set lambda, it's just split lambda into lambda 1 plus lambda 2. Yeah. Right.
For arbitrary V1 and V2 then.
Yeah. So, but in this situation, we are well off because actually we can solve, and I know that this is kind of, I don't know, hurting maybe, but this is just what I wrote before, just emphasizing that for each subminimization problem, because I have this additivity property, I can apply the same strategy that I apply to the whole problem to solve it. So in this case, for L1 minimization, what I do is I compute the minimizer on each of these subspaces by self-thresholding, for example. Okay, and what you can show, or what actually Massimo showed, is that that with this procedure you're converging even strongly to a minimizer of the functional on this whole index set lambda. Okay, so this additivity property really gives something to us which is crucial. What happens if we don't have this? So what happens if we are now considering the minimization problem with the total variation, and I want to do the same? This is just saying, again, what I want to do. And for now, I consider a splitting of this Hilbert space H, which is in our case now L2 of omega. I consider a splitting of L2 of omega into L2 of omega 1 and L2 of omega 2, where omega 1 and omega 2 are there's a disjoint decomposition of omega, like I've written it here. Okay, and I want to apply such a strategy.
Can I ask you a naive question maybe? So when you write down the algorithm, it seems like U2 to do its job needs to know the input of U1n plus 1. So
I will come to this.
Because if we have two processors, it's like, and one is computing the minimizer of U1 and the other of U2, it seems a bit strange to have to wait that processor 1 is done to actually start working. We want them to work together.
So what happens if I'm actually, so there exists a parallel
So what I
version
would
of
like,
this.
I'm asking is,
I have the U1n here, for example.
Yeah.
Yes. So the parallel version would be U1n here. And then I have to communicate after each iteration. I have to communicate, but also all the theory, all the convergence result that I'm going to tell you in a few seconds, they also hold for the parallel version.
That's what I was getting to, which is that I don't want the convergence to break if we have U1n and not U1n plus 1.
It will not break down. What you have to do with the parallel version, if you have more than two subspaces, okay, if you have U1 plus U2 plus U3, for example, you have to weight the update a little bit. So that's the only issue. Actually, numerically, so to get the convergence theorem, numerically it seems that it's still converging, even if even if you do it differently. But you have to weight in the sense that you have to reweight with the previous iterate of U on the whole domain. So you have something like U2 of n plus this new update divided by the number of subdomains.
A relaxation.
Yes. Yeah, and this you need to still guarantee that under this iteration your functional j is decreasing. So this is also something that comes out from the convergence result, because you want that your functional j is monotonically decreasing. So anyway, so now with total variation minimization, we don't have this nice additivity property anymore, and I mean, actually it makes sense that we don't have it, because we somehow have to capture what happens across the interface. Because, as I said, minimizers of the total variation can have jumps, and jumps might cross the interface, and you want to record these jumps, and this is this additional interface term that you get. So there is no straightforward way right now to use the iterations as before for the L1 minimization to solve the local problems, because we can have discontinuities across the interface. And the known results for domain decomposition also do not cover the situation. So what do domain decomposition results usually cover? They cover smooth problems, okay? Smooth problems are well understood. And they also cover non-smooth problems, but non-smooth problems with this additivity property. So none of these approaches can be applied to our situation because we are non-smooth and non-additive. And there are actually even counter-examples in the literature that a subspace correction method or a subspace decomposition method will not work in all situations. So there are counter-examples that a decomposition actually will not converge to global minimizer. So is there no hope? Well, there is, because otherwise I wouldn't be here. And what is the strategy? What we are going to do? So what we are going to do is, the question is, how do we solve each of these subproblems here? So we want to minimize J of U, where U is split in U1 and U2. We want to split it, say, in the first subproblem only over the subspace V1. And the first thing I'm going to do is I approximate this minimization problem by a sequence of minimization problems which are easier to solve. And J1 of S is something that is sometimes called surrogate functional. So we approximate the minimization of J by minimizing a sequence of so-called surrogate functionals, or if you're coming from another community, maybe this can be also recaptured in the setting of the Douglas-Redford splitting, where these problems are now easier to solve because what I do is I actually replace the functional J of U, which is alpha times variation of U on omega, plus this TU minus G. I replace this by Js of U, say UK, which is alpha du of omega is the same as this, plus, and now I have something like U minus, and I think it's T star UK minus T UK minus G. Okay. So what I do is, and I'm only making this short, what I do is I reformulate the minimization for this J of U over U. I reformulate this into a sequence of minimization problems, where in each minimization problem I construct a minimizer UK plus 1 and put it as a right-hand side to the next minimization problem. And the advantage now here is, in order to compute the minimizer of this functional, you don't have to invert an operator. Okay, so you basically just, so you have an operator here which is just the identity. So you have moved the information of your operator to the right-hand side, and this is the first simplification that we do. We construct a sequence of minimization problems where the operator T now in our problem is moved to the right-hand side of my data fidelity term. And now I reformulate this problem, which is a constraint minimization problem. We are minimizing over this space here. We are over the subspace V1. We are reformulating this into a minimization problem over the whole Hilbert space H, only looking at potential minimizers, or restricting our admissible sets of minimizers to those whose projection on the second subspace is 0. Okay, this is just the same as this, just that we have reformulated this now for the whole space H. And then we can iteratively solve this now, this minimization problem by reformulating it as an unconstrained minimization problem. And this unconstrained minimization problem, we can apply, whatever you want to solve this. One example how we might want to solve this is by what we call oblique thresholding. And it basically consists of two parts. The one is just the usual iterative thresholding for the total variation. And the second one, well, with a Lagrange multiplier for this constraint that I wanted my solution is 0 on the other space. And I have to, I need another iteration for this Lagrange multiplier, which is basically taking care of the interface condition, okay? Of the interface that I might have jumps across the interface. So I cannot forget about what is happening on the other side completely. Luckily, this iteration here, and that's why this is still relevant for practical applications, this iteration here, this additional iteration for what is happening on the other side, we can restrict this in practice to a small stripe around the interface. And that's enough. Okay. Yep.
Can I ask you what is oblique thresholding? Because the prox function of the total variation is not known in closed form, right?
Well, what we do actually here is to compute this. We apply Chamboll's method.
I see. Okay. So this.
So we approach the projection via a fixed point iteration.
An inner loop.
We have an inner loop for this as well. Yeah. Yes. All right. So what can we show about this? First of all, the sequence of minimizers that comes out of this alternating algorithm will produce a sequence under which the functional j is monotonically decreasing. Nice. The minimizers, the elements of the sequence are approaching each other in the Hilbert space norm, and the sequence is also converging in the topology that is given to us by the regularizers. In our case, it's also weakly converging in BV, which is not very strong, which is very weak actually. So it's weakly star converging in the space of bounded variation functions. But, and that's one of the disadvantages of this decomposition as we have done it right now, the convergence to a minimizer of J is only true under additional conditions, under additional assumptions on how we are decomposing, okay? And that's something that we weren't quite so satisfied with. That's why also there is a continuation, but let me first show you some first results. The nice thing about, well, that we actually don't have such a good result here in theory is that in practice it still seems to work. For just, you just have a signal which is a jump from -1 to 1, and your interface is this red dot here. So we wanted to see, if we now penalize the total variation of this signal here, if the jump is preserved, and it's actually preserved. It's just, doing what total variation is usually doing. It's decreasing the size of the jump. And another example in 1D, you have an interpolation problem. So you have your signal given here and another part of the signal given here. And here the signal is missing. Okay, so here you don't have any information. So you can also solve an interpolation problem like this, and you get, you get something that is behaving okay-ish at the interface. Just to show you some 1D examples, because in 2D you often don't see these things. And unfortunately, you can also not really see this, but what we have here is actually, this is a boat on the cam with a dog on top, and that's why, and this image is distorted by writing, by superimposed writing. And again, what we are going to solve is an interpolation problem, which is also called image inpainting. We want to remove the writing here. You can also think about this as having given your image only in the pixels, which are not the writing, and you want to find the image in the inside of the writing. And we split the problem here into two domains, omega 1 and omega 2. So the red line here is the interface, and and we can apply total variation inpainting to this and get this result. So if the beamer would be clearer, you would see that there are no artifacts at the interface. But yeah, I guess you have to believe me right now. So anyway, so we are not quite satisfied. Yes.
Can I make an amusing comment?
Mm-hmm.
Which is that some Hollywood companies use this technology to remove things on the scenes of movie scenes. So, for example, if you see Angelina Jolie and so on, when she jumps in the air, there's a cable pulling her up. And it removes this digitally by some kind of sort of variation idea.
Okay, nice. So it's actually applied.
I've learned this from Hollywood people.
Since we weren't so quite satisfied with what we could theoretically prove, we are going to simplify our situation such that we can prove more. So that's the usual thing, right? So the first thing that we do is we look at the finite dimensional case, we discretize our functional, and we justify this by saying, okay, first of all, in practice, we anyway only deal with discrete versions of the functional. In numerics, for example, we only consider the finite dimensional case anyway. And the other maybe nicer justification is, well, whatever we can prove for this functional J in the discrete setting, in some sense also goes over to the continuous setting, because we have a terminology which justifies this, which is called gamma convergence. Okay, so we have that if we let the step size of my discretization here go to 0, this functional J converges to the continuous functional in the sense of gamma convergence, which is, for example, giving you the property that minimizers of the discrete functional are converging to minimizers of the continuous functional when you let the step size go to 0. So things like that, they're somehow preserving the structure and what you're proving in this setting, also for the continuous case. So it does not change the nature of the problem very much. That's why we're doing this. And then the other thing that we're doing, we're going away from the orthogonal decomposition. We hope that instead of considering a splitting into two orthogonal domains, into two disjoint domains, omega 1 and omega 2, if we do this with a small overlap, that we get some additional information such that we can say something about the convergence, something more about the convergence. Okay. So this is just again saying that we don't have a perfect splitting of the total variation. I'm not going to say this here. The alternating minimization now changes only in the sense that we are minimizing over two overlapping domains, omega 1 and omega 2, where we have this additional constraint here that on the interfaces gamma 1 and gamma 2, the minimizers u1 and u2 have to be 0 respectively. This is a technical assumption that we have to use in the proof. So what can we prove? We can prove the same things as before. Okay, we can prove the same things as before for this iteration. But now we also have convergence. So we have that the sequence of iterative solutions of my domain decomposition algorithm are actually converging to a minimizer of the functional on the whole domain. And that's actually the first rigorous proof of convergence of a domain decomposition method for this kind of non-smooth, non-additive situation. Okay? And just a few points in the proof. Basically, what do you have to show really for this last bit to show that my subspace minimizers are actually giving you a minimizer of the functional on the whole domain? And here, how we do this is we try to fit the characterization of minimizers on each of the subdomains in terms of the subdifferential. Okay, so we are characterizing minimizers as elements of the subdifferential of J in this form. So again, you shouldn't read this, but you can read this, for example, in Luminita Wese's paper, where she talks about how you characterize elements in the subdifferential of the functional J, or in other words, potential minimizers of J. And you want to stitch together these two characterizations that you get on each of the subdomains. You want to stitch them together to a characterization of a minimizer of J, or an element in the subdifferential of J on the whole domain. Okay, and this, unfortunately, but fortunately now that we have this, works only for the overlapping part, because it gives us really that, it really gives us that if you add the two limits of the subspace minimization problems, you get that adding those up, you get a minimizer of J on the whole domain. All right. So I cannot be more specific here, otherwise it would be a pain, I guess. So sorry. So there is a natural parallel version of this algorithm. Of course, we can apply the same subspace decomposition strategy to other regularizers, like we have seen L1 minimization or L2 minimization, H1 minimization, you know, whatever you want. It just can get easier, basically. The same strategy can be applied if you, say, don't have an L2 fidelity term, but you have an, say, H-1 fidelity term, which can be important in some applications in image denoising or image decomposition, where you look at these kind of fidelity terms rather than L2. And yes, some examples. Again, this interpolation example. So this is the signal here, this is the given signal here. Here you have a gap, and you get this interpolation. And here, basically, I just wanted to show you that we are not, you know, the theory is not cheating. It's really that the functional for all, so here we have the curves for the functional J of u. So these are the values of J of u after a certain time, after a certain number of iterations, for various overlaps of my two domains, and they are all converging to the value, the minimal value of the functional J, which is this here. Okay, so just to show you that this actually also works in practice. And again, we can do this also in 2 dimensions, where here we have the interfaces. We always have 2 interfaces between 2 subdomains, gamma 1 and gamma 2, denoted by these red and blue lines, and we can do the same reconstruction as we have done it for the non-overlapping. All right. So very quickly, what we have done now in the physical domain, nothing prevents us to actually apply this, not physically splitting the image domain into 2 subdomains, but splitting the space, in our case L2 of omega, into different subspaces. And the thing that we looked at is multi-resolution analysis. So assume that your function u that you want to reconstruct has a wavelet expansion in this form, where psi lambda is your wavelet basis, and you assume that the coefficients u lambda you only have a few non-zero u lambda coefficients, meaning that this expansion here is sparse. And then you can, having given a scaling function phi, you can generate a multi-resolution analysis of your space L2 of omega, where you want to minimize your functional J in this form, where you decompose L2 of omega basically as an orthogonal decomposition of the wavelet spaces corresponding to different corresponding to different kinds of of low and high resolution analysis of your multi-resolution representation. And then the idea is, if we again stick to decomposition into two spaces, we decompose L2 of omega into V0 and into the orthogonal complement of V0, into the direct sum of the wavelet spaces Wj. And then what we do is we minimize alternatingly J on each of these two subspaces. So first of all, what you immediately might object is, okay, we have not reduced the dimension of our problem, because the dimension on each of these problems is the same, right? We just look at the low and high frequencies, basically. But the dimension in the physical domain where we are actually solving this is the same. But what we will see is we will again apply the same strategy here. We solve each of these sub-problems and then add them together again. And in particular, what we do is we additionally precondition each of these subspace minimization problems by the same thing that we have done before, by the surrogate functionals here. But now we are constructing these surrogate functionals by introducing an additional sub-band specific parameter alpha I, which makes basically the operator T on each of these subdomains better conditioned. Okay, so this is basically what we do here. So why should this work? I mean, why should we have any payoff of doing something like this? So the first thing that we got motivated by is the work of Wonisch and Unser, where they did something very similar to what Massimo did for the L1 minimization case, but they splitted the wavelet coefficients. Okay, so as we want to do it now, and they applied this for image deblurring, and they showed that this splitting procedure has a tremendous preconditioning effect. And I again don't have time to talk about this, but this is one of the motivations that those guys have actually already, given us reason to believe that this works for one minimization. And these guys have given us reasons to believe that this also applies for total variation minimization, because actually minimizing the L1 norm of the wavelet coefficients is nearly equivalent than minimizing the total variation of a function. Okay. And this brings us to the idea to apply this for total variation minimization, and that's the result. And actually this was very, well, I'm not so experienced with this multi-resolution analysis, but this was very, very, very surprising for me. So you have a blurred image and you restore it, and here you split into n subspaces. Okay, so here n is 1, 2, 3, 4, 5, and so on. So this is when you don't split, basically. N is 1, you just de-blur the image on L2 of omega. You must wait for 525 iterations until we reach a certain accuracy. Okay, until my functional, we always stop if the functional j has a certain value. And the seconds we have to wait is 40 CPU seconds. If we just split into two, and here I don't even parallelize anything, this is the sequential version, we only have to do 12 iterations instead of 525. And this is 2.6 seconds. And it doesn't decrease so much anymore when you do more and more splittings. And at some point, the number of iterations kind of stays the same. But this is already a tremendous acceleration that you... It's because of the preconditioning. Mm-hmm. Yeah. Yeah, because here I didn't parallelize even. It's still sequential. All right, and also the nice thing about doing this for the wavelet space, or for decomposition into wavelet spaces, is that we have, from our general theory, we know that we don't have in general convergence to a minimizer of the functional j, right? Because again, we have the orthogonal decomposition. But we have an explicit condition when the limit of the sequence is actually a minimizer of the original functional. And this condition here is given by elements, by terms that appear in elements of the subdifferential of J. And I again don't have time to explicitly tell you what these guys are, but we have a hand on these terms here, and we can numerically follow what these terms are doing and if they're equal to each other, because if they're equal to each other, we are actually at a minimizer of J. And it's nice because they're actually converging to 0, which is a good sign. All right. Just very quickly some numerical results. And I think I will not have time to talk about the parallel MRI example, but let me just keep talking about image in painting, image restoration. So you have an image which is very large, 5,600 approximately times approximately 3,700 pixels. And this picture is superimposed by this red writing, which we want to eliminate. So the operator T, by the way, in this case, is the characteristic function of the image domain outside of this writing. So you only take into account in the fidelity term, which is given to you. Okay. And then we look how long we have to wait until we get an image restoration result, which is good enough for us. And we do this without a splitting. We do this with a splitting in 4 domains, and we do it with a splitting in 16 domains. And here I have to say that that when we don't split at all, we could have even waited longer. Okay, we actually stopped the process after 1,000 iterations because it just the convergence got slower and slower and slower the longer we waited, and we didn't reach the accuracy that we wanted to have. So here we wait 6.5 hours. We didn't even reach the accuracy that we want to have. With 4 domains, 1 hour 3/4, and with 16 domains, half an hour. So yeah, you see it's a linear decrease with the number of domains. So this is already very good for domain decomposition people, and they were very surprised about this actually. So, okay, I will not talk about the parallel MRI. Here just to tell you, this is the result with 4 domains, this is the result with 16 domains. So, yeah, again, because it's black, you don't really see it, but it doesn't look different. All right, so maybe one more thing. You can speed up these iterations by terms of Bregman, and this is joint work with Stan Osher and Andreas Langer now, where we, instead of applying the oblique thresholding idea to the subspace minimization problems, we solved them by a nested Bregman iteration. So that's the basic thing. And for this image here, which we split into 4 domains, we looked at the computational time with oblique thresholding and this new Bregman iteration, this nested Bregman iteration method, and we looked at the CPU time per iteration, per domain decomposition iteration, and it's more or less 3 times faster doing it like this. But this is more, like going into the details now and trying to improve it. So, all right. So let me skip all this and go to the end. So what I've shown you is an algorithm, a subspace decomposition algorithm, to deal with large-scale imaging problems. In particular, solving imaging tasks with total variation minimization. And we have applied this both to the physical domain and to a decomposition into wavelet subspaces for image deblurring. And I've presented you some application. Well, actually, I've presented this an application for image in painting for a very large image. And just for you, if you want to try out some of the numerics, they're all available, both the parallel version of the code and And the sequential version of the code in 1 and 2D are available on my webpage. So thanks for your attention.
So we have time for questions. Yes, please.
For your in-painting example, you don't have blur, right? The one you showed with the words on it.
No.
Okay.
Yeah. So
Can you deal with blur?
I've shown you examples for de-blurring, and I've shown you examples for image in-painting separately to each other.
But I'm saying for in-painting example, can you deal with the blur like model? Is it a-
Additionally, you mean additionally?
Yeah.
So you have an in-painting plus de-blurring?
In other words, it's a blurred image, but some bits missing.
Yes, you can. Yeah, but then you would have to modify your operator T to something which is not the identity outside, but which is the kernel of your blur operator. You know, which is a blurring operator with some kernel with which your image has been blurred. So usually, for in-painting, you would have the T. Okay, it's just the characteristic function of, so say you have here the domain omega of your image, and the missing parts in your image are D, okay? So it's the D is say the union of all these letters which we have seen before in the writing. Then the T would be the characteristic function of omega without D, right? Everything which is outside of the missing domain would be the operator. This is the usual, this is the pure image in painting. And then if you would have de-blurring, you would have something like T is some blurring operator, say B, involved with omega without D. Okay, so we would have something like this, and B is a blurring operator.
Another short question is on your surrogate, this function here behind you.
Yep.
So essentially, you kind of introduce a lagging to the blur operator. You mainly like do the iteration on denoising, yeah. Let the de-blur to catch up somehow.
You mean how we construct this for de-blurring, or?
Well, I'm trying to see how it works, because de-blurring is not like heckled directly; it's all indirectly coming in, isn't it? It's a T operator, yeah. That's
Right.
global, yeah. That's global operator.
Ah, okay, this you mean. That's a very good point, actually, for the subspace decomposition, right? Right. So what you do, and that's actually the same. So that's maybe one of the things that you have to keep in mind. That's the same if T would be the Fourier transform, for example. Right? This is the same. You cannot split the Fourier transform into your domain decomposition patches. But that's a good thing that this guy here is on the right-hand side, because you have to compute the Fourier transform of your whole solution after each domain decomposition iteration. Okay, because you have to compute this right-hand side.
That's what I mean.
But afterwards, you can restrict this guy to omega 1 or omega 2 or whatever. But actually, yes, you have to compute it after each outer domain decomposition iteration. You have to compute it.
Kind of create a lagging, yeah, let it catch up. Yeah.
Right. Mm-hmm.
How much inter-process communication is there in your parallelism?
For the domain decomposition now, if you have these non-overlapping domains, what you have to do is you only have to communicate for the image restoration now again. Okay, so let's say we have an operator T, which is just this guy here. You only have to communicate some part of each of the subdomains across the interface. So some small stripe from the neighboring subdomain to the other subdomain after each after each iteration. You have to do this. Again, this communication will increase if you have an operator T, which is, for example, the Fourier transform, because then you have to communicate the whole solution to all of the subspaces.
So it's more shared memory than distributed.
Yeah.
what is connection between your work and say what Emmanuel told us, just ideological? So in the Emmanuel case, you have just sparse information, yeah, and you would like to recover it from as sparse, just another part of information as possible. So I think it's not the case in
Well, it is the case, for example, when you. So what you assume here is, so T could be also something what Emmanuel said. For example, when you look at an MRI problem, what T would be is just a sample of the Fourier transform of your signal. So in this case, it would be this. Well, it would be actually the same as the problems we have seen in the last days. Actually, it fits very well in the last lecture.
But you mentioned that G is of huge dimension, yeah, and then U is even, I mean, but U is just composed of some.
Is then just T is then just again this fat and short matrix. Yeah.
Okay.
That would be this case.
Okay. So
Does your metastronic depend on the choice of a decomposition?
That's a very good question. So a lot of domain decomposition people actually ask us this because it seems, and that's where I'm not an expert. See, so I'm more coming from this, optimization community. But a lot of people ask us, and this would be something interesting to go into. Apparently it does. It does. So domain decomposition, the speed of convergence of each of these domain decomposition minimization problems very much depends on how you decompose. But we have not looked at this. Yeah. But that's a very good point. Mm-hmm.
okay.
For the deep blurring example,
Mm-hmm.
how do you compute the precondition parameter alpha J is in your algorithm?
Okay. So what we do is we compute the alpha I as the operator norm of the blurring operator, just conditioned on the subspace, on the specific subspace where I want to minimize, and the synthesis operator, right, for the wavelet case now. So I compute the alpha i's. What I had is the alpha I was the operator norm of TVI and the synthesis operator squared. So I want to basically what I want is I want that the operator, well, the kind of operator that I have in the problem that I'm solving. Then, if I normalize like this, I'm normalizing such that the new operator T has a norm which is smaller than 1. So basically, here it should be greater. So you want alpha I to be greater than this. So you're reweighting your minimization with the operator norm in each of the subspaces.
Okay, so thank you again, and